Hello everybody, this is Rob Swatsky from the York campus of Hack, and welcome back to my Biology 121 Anatomy and Physiology 1 course. This is podcast 2.5a, Organic Molecules and Functional Groups. Even though there is an incredible diversity of chemical compounds found in the body, they can all be placed into one of two different categories, inorganic or organic. Inorganic compounds typically aren't made up of any carbon atoms and have a simple structure. They are small compounds that consist of a few atoms held together by either ionic or covalent bonds. Examples of inorganic compounds in the body include water, the body's most important and abundant inorganic compound, carbon dioxide, CO2, and many acids, such as carbonic acid, H2CO3, bases, such as bicarbonate ion, HCO3, and salts, such as NaCl. In contrast, organic compounds are carbon-based, with chains of carbon atoms making up a main portion of their chemical structures. In addition to carbon atoms, hydrogen, oxygen, nitrogen, sulfur, and phosphorus atoms are also commonly found in the structures of organic compounds. Most organic compounds are quite large, consisting of dozens to thousands of atoms, and have complex structures held together by covalent bonds. The largest of these organic molecules are called macromolecules, which are made up of smaller organic molecules. Most macromolecules are also polymers, which are long-chain molecules formed by covalently bonding together many small building block molecules called monomers. When you think of a polymer, imagine a child's plastic bead necklace, where the entire necklace is the polymer, and the individual beads that are pushed together to assemble it are the monomers. Some examples of synthetic, laboratory-made polymers include polyethylene, which is made out of repeating chains of ethylene. Polyethylene is common in many types of plastic bottles and bags. Another example is polystyrene, used to make styrofoam cups. It is made out of repeating chains of styrene. Some natural polymers found in the body include the polysaccharide sugar glycogen, a branching polymer made out of glucose monomers that is stored in the liver and muscles. The body's proteins are also polymers, made out of chains of amino acid monomers. Because of their larger size and complexity, organic compounds also possess many unique properties and perform many of the body's important functions. Examples of organic compounds that we'll be learning about in this chapter include carbohydrates, lipids, proteins, nucleic acids, and adenosine triphosphate, more commonly known as ATP. Organic compounds are carbon-based. But why carbon? Why aren't organic compounds built around atoms of other elements like potassium, zinc, or aluminum? One main reason is that carbon has the ability to easily bond with other carbon atoms to form large molecules having an incredible variety of unique structures and functions. A carbon atom has 4 valence electrons in its outermost shell, which means it can form multiple covalent bonds with other atoms to form straight and branched chains or ring structures. When carbon atoms bond with other carbon atoms, they form a chain called the carbon skeleton. If the carbon atoms in the carbon skeleton are bonded to hydrogen atoms, a compound called a hydrocarbon is formed. In addition to hydrogen, there are other specific atoms or molecules attached to the carbon skeletons of organic molecules. These are called functional groups, and they give the compounds they are attached to distinct chemical and physical properties. We can use functional groups as a way to classify different organic molecules, and because they react in specific ways, they help us predict a molecule's behavior. Some common functional groups include hydroxyl groups, amino groups, carbonyl groups, and carboxyl groups. A hydroxyl group consists of an oxygen atom bonded to a hydrogen atom. Hydroxyl groups are common in alcohols, and you can remember this because the word alcohol contains the OH group as part of its name. An amino group consists of a nitrogen atom bound to two hydrogen atoms. Amino groups are found in the structure of all amino acids. A carbonyl group consists of a carbon atom double bonded to an oxygen atom. Chemicals with carbonyl groups are classified based on the location of the carbonyl group in the carbon skeleton. Ketones have a carbonyl group within the carbon skeleton, while aldehydes have a carbonyl group at the end of the carbon skeleton. A carboxyl group consists of a carbonyl group bonded to a hydroxyl group and form acids called carboxylic acids. Carboxyl groups are also found in the structure of all amino acids. We will encounter these and other functional groups as we further explore the body's organic chemistry. Because of the large size of organic molecules, we often abbreviate their structural formulas when we write them out. Here is the complete structural formula for the sugar glucose, with all of its atoms included. The dashes between atoms and the lines connecting the atoms making up the ring represent single covalent bonds. Now here is the structural formula of glucose written using the standard shorthand. To simplify the diagram, we leave out the symbols for single hydrogen atoms and for carbon atoms at the points where two covalent bond lines intersect. Thanks for watching, and please feel free to contact me by email at rjswatsk@hack.edu if you have any questions or comments about the course.